The first thing that I would say you have to memorize or you have to know is that when we talk about apparent weight, that a person or an object experiences, it's always the applied force upward. So we're talking about situations where you have vertical acceleration. That's the only way you're going to get a weight that is apparently different than what we call the true weight, and I will get to a review of what the true weight is in a second. But objects that accelerate up have a different apparent weight. They feel different weight-wise than they do when they're not accelerating up. Objects that accelerate down, same situation. I would say the second thing you need to know, and I don't know that this is a memorization thing so much as a life experience thing or a common sense thing, is that when you have an acceleration up, your apparent weight is greater than your true weight. And again, we had a discussion yesterday about what does it mean to say an object has a particular true weight? There's nothing about an object that makes its weight some kind of magical thing that's always a true weight. Weight changes depending on the planet you're on, depending on the environment that you're in. When we talk about true weight, we're referring to the force due to gravity in that environment. Mass times 9.81 if you're on the surface of the Earth or close to the surface of the Earth. On the other hand, if you were accelerating down, you know that's the case because the apparent weight is less than what's called the true weight. And I take it back that I don't really believe those last two statements are memorization things, because you should understand that the only way you can be accelerating up is if the applied force upwards is more than the force of gravity downward. And if the applied force is the apparent weight, then the apparent weight is more than the force of gravity, which is your true weight. So I'm going to give you a couple of diagrams here. Some of you are writing this down. That's good review stuff. If I were to talk about, and let's go with the classic kind of example that you're in an elevator, right? And there is a scale in the elevator that you are standing on. So you're standing on a scale. This ought to be good. Well, maybe that's not you. It's some alien. I don't know. So when you draw a diagram here for an object that's accelerating up, if the object is accelerating up, then the force due to gravity on you is, of course, down, but the applied force to your feet by the scale in the elevator is up, and it's bigger. This is what we're talking about. This is a acceleration that is towards the sky. On the other hand, this is an acceleration towards the ground. And in both of these cases, this is the force due to gravity, and this is the applied force. But the point I want to make is that this is the apparent weight. Right? Whatever that applied force is, that's the apparent weight. The true weight is whatever that is. And we're going to do a fair amount of review today about Newton's second law. This is just a very specific example of applying Newton's second law. I'll remind you what Newton's second law is. Newton's second law says F net equals ma. And, I think it's really important that you remember here net force is a vector and acceleration is a vector. Okay? But, and this gets a little bit tricky, and it's been a while since we've talked about this, when I build an equation for all of these, I drop the vector symbols by building the direction into the equation. So, for example, F net means to add these forces together. Well, how do I add forces that are in opposite directions? I subtract them. I take the bigger minus the smaller. So what we end up with for this situation is the apparent weight, which is the applied force, minus the regular force of gravity equals ma. And the vector symbols are gone now because I've built them in. I've said, well, this is up and this is down, so I take the bigger minus the smaller. And over here, I include the directions in this formula for F net, but when I build the equation, I just look at this and I use common sense. The force of gravity down is more than the applied force up, so the net force would be found by taking the force of gravity, which is bigger. I'm going to pause and correct what I just said. The net force would be found by taking the magnitude of the force of gravity, which is bigger, minus the magnitude of the applied force, and that's equal to ma. And that's how you calculate apparent weight. Or it's also nice here that apparent can be abbreviated APP and applied can be abbreviated APP. But that's the relationship between the true weight, the apparent weight, and the acceleration if it's accelerating up or if it's accelerating down. The last thing is, of course, if it's not accelerating at all, which means it's moving at a constant velocity, or it's not moving at all, your apparent weight is your true weight. So let's back up now and take a look at these questions. Does anybody have any questions you would like me to go over from the assigned work? All right. We're going to spend some time doing a quick review here. And I'm going to be talking about each lesson. There's a lot in this unit, and I don't want you walking into the exam on Friday ill-prepared. I want you to be as prepared as possible. So what did we do in lesson 2.1? Well, 2.1 was called The Nature of Force and Newton's First Law. I'm not going to write down everything. If you want, you can follow along in your review package here and put the review notes someplace else, like in the margin, or if you had a different color pen, you can do that. If you want to just copy down what I'm going to put, that's fine. But my idea here is to bring back these memories because it's been, 3 weeks at least since we started this. One of the things we did in 2.1, it was the main focus, was we looked at Newton's first law. Of motion. And Newton's first law of motion, I'm not going to write it down, it's in your notes. This is a review package that we're talking about here. You can take a look at that and go, what is that? And go find it in your notes if you need to. Newton's first law talks about whether objects accelerate or don't. That's the bottom line. And the bottom line is objects accelerate if the net force is not zero. And there's so many ways that I could explain to you what that means. The object will accelerate if there's an unbalanced force acting on it. So if I'm driving a car and it's accelerating, what that means is there's a forward force that's not entirely balanced by some backward force. However, there will be no acceleration if F net is 0. What does that mean? And we drew vector or free body diagrams of this in one of the first examples. You can see, if you're looking in your notes, at the diagrams of the cars that we drew. What does that mean? It means that if I'm driving along with a constant velocity, no acceleration, all of the forces are balanced. Is there a force of gravity acting on the car? Absolutely. But it's balanced by a normal force. Is there a force that the engine pushes the car forward with? Definitely. But it's perfectly balanced by all of the forces of friction in the opposite direction. Friction between the tires and the road, friction between the moving parts of the car, friction between the surface of the car and the air. The only other thing we did in this lesson is finding net forces. And I will just let you know the reason why we did this in this lesson was to get you used to adding vectors. That's what we were doing. We looked at reviewing of how to add vectors. And throughout this unit, we kept going back to that and saying, basically, everybody, if you have forces that are in the same direction, you simply add the numbers together. If you have forces that are in opposite directions, you take the numbers and subtract them. The numbers are what we call the magnitudes. If you had forces that are perpendicular to each other, you draw them tip to tail and do a right angle triangle analysis. We've done that 30, 40 times in this course so far. Pythagorean theorem to find the hypotenuse, tangent to find the angle. If the forces are in any other orientations, then you take each force and break it into a horizontal and a vertical component, collect all your horizontal components together under one horizontal vector, all your vertical together, then draw those two tip to tail. But that was lesson 1. Okay? Lesson 2 got tricky. Lesson 2 dealt with static equilibrium. And the questions that were assigned and the questions we did for examples are questions that are fair game for the exam. An object in static equilibrium means multiple forces cancel. And you did a lab on this. Remember the lab we did? Where you had that metal ring and it was being pulled in two different directions by two forces. The sum of those two forces was balanced by some third force in the opposite direction, which we call the equilibriant. But I will just remind you here, the types of problems we're dealing with are like the hanging sign questions. And I will just draw one here. We won't worry about doing it, but maybe what I have is a wall and an overhang of the roof, and I have a cable coming down to a sign here, and I have a cable going over to a sign here, and the sign is hanging by this elaborate set of cables. The important idea here, everybody, is that this force that one cable is applying, and I'm offsetting it into my diagram so you can see it a little better, plus this force that the other cable is providing, plus the force due to gravity acting to pull it down, have to all add up to give 0. And I hesitate in muddying up this diagram too much, but on this diagram, this upward force that I'm going to highlight in yellow, that vertical component of that angular tension, must exactly be equal to the force of gravity. So if you knew the force of gravity, you could determine that upward component. The horizontal component of that angular tension, which is this, has to exactly equal the tension in this cable. So that's the classic hanging sign question. The other type of question I could give you would be a question where I give you two forces and ask you, what is the equilibriant? And if I give you two forces, let's just say that I have some object. It doesn't matter what the object looks like. There's the object. And I tell you that we have a force of 40 newtons at an angle of 30 degrees here, and a force of 50 newtons at an angle of 60 degrees here. If I say to you, what is the equilibriant? What I am asking is, what is the force that would be in the opposite general direction that would cancel those out? And in order to answer that question, you would add those two forces together. Whatever number you got would be the value of the equilibriant, and whatever direction you got, the equilibriant would be in the opposite direction. And that was the purpose of doing that lab. So that was 2.3, or 2.2. 2.3, we moved on to Newton's second law of motion in a very limited way. This is Newton's second law of motion. And the reason why we looked at it in a very limited way was we weren't worried about ramps, we weren't worried about friction, we weren't worried about vertical motion. We were essentially worried about objects that are on a horizontal surface where there are horizontal forces acting on the object. So maybe there is an applied force. Now, I'm going to go back on my word here. I said in this lesson we weren't worried about forces of friction. Let me rephrase that. We weren't worried about how you calculate the force of friction. But we were concerned with situations where you had an applied force in one direction and a force of friction in the opposite direction. And I made the point when we first learned this, I said, this is not Science 10 or junior high science. This is not, oh, F equals ma, find a force and put it in for F. It's look at the diagram and say to yourselves that in this case, F net equals the applied force forward minus the force of friction backwards. Now, put absolute value signs there because this is what I mean when I said earlier we build the directions into the equation, into the statement. How do we add forces that are in opposite directions? We subtract their magnitudes. And this is how you would solve these problems. You would go ma equals the magnitude of the applied force minus the magnitude of the force of friction. And only because I feel I need to, you understand that me not writing the vector symbol is the same as me writing the vector symbol with the absolute value signs? Means the same thing. That was essentially 2.3, Newton's second law. And then we walked away from Newton's second law, and we did Newton's third law, which basically says, and this became different, we're not talking about just a single object. We're talking about two objects which basically come in contact with each other, a bat and a ball, or firing a bullet from a rifle. They're pushing off of each other. And what Newton's third law says is that the force on A by B is equal to the negative of the force on B by A. You know, we put this in words. I don't know that I ever wrote this in your notes or in any of the lessons. We typically put it in words and said, you know what? Newton's third law says when two objects push off of each other, they apply equal but opposite forces. And there were a couple of types of examples that we looked at there. What I'm going to do, however, to abbreviate this, because I want to give you time to work on this stuff today, is I'm just going to say, see the examples. And I will tell you right now what the two classic examples are. A person on a skating rink throws a bowling ball in one direction with a speed. How fast do they move backwards? And there's a way that we did that, and it's in your notes. The other type of problem is the one where we had boxes resting against each other, and you push on one box, or you push on all of them, and you have to find the force that box B exerts on C, or the force that box B exerts on A, or the force that your hand exerts on A, those types of questions. Then we spent some time before we actually got to applying Newton's second law in more detail. We spent some time learning about frictional forces and about forces due to gravity. So, 2.5, 2.6, I'm going to condense the next few lessons down. And 2.7, I mean, think about this, everybody. 2.5, we spent a whole day basically, learning about this formula. There's more to that lesson than that. But that's what that lesson was about. How do you calculate the weight of an object? I just go under the assumption now that if I tell you you have a 12 kilogram mass, you know what the weight is. You can find the weight. We don't need to review that, I hope. We also in here, and you are going to be asked about this on your exam, talked about mass versus weight. Now, 2.6, it's interesting because everything is building up here. All of these little things are going to become useful when we get to 2.8 and 2.9, but they're just little things. 2.6, you know what we did with 2.6? We learned about this formula. But in 2.6, all of the surfaces were horizontal. Right? So if the surface was horizontal, then the normal force was the force due to gravity. Remember that? However, in 2.7, we branched out and we said, well, let's talk about inclined planes. And in 2.7, if we had an incline, then the normal force was equal to the component of gravity that was perpendicular to the ramp. And that's it. That's what we did in 2.7. We didn't even, in 2.7, really worry about working with acceleration. There might have been one question where we did. But I want to summarize 2.7. With this diagram. That when you have an object on an inclined plane, as long as you are not applying any force to it, the following are the forces acting on that object. There is a force due to gravity that's perpendicular to the ramp. There's a force due to gravity that's parallel to the ramp. There's a normal force, which is balancing the force of gravity perpendicular, and there is also a force of friction. So this is the force due to gravity parallel to the ramp. This is the force due to gravity perpendicular to the ramp. This is the force due to friction, and this is the normal force. And then we got to 2.8. And 2.8 was at least a 3-day lesson. .8 was, I'm going to call it F net equals MA revisited. We said, look, I've taught you all of the tools you need. I've given you all of the tools. You know how to find weight. You know how to find force of friction. You know that F net equals MA means all of the forces have to add together to give MA. So we looked at the following situations. We looked at cases where you have an object accelerating up against gravity. We looked at situations where you have a different object accelerating down, even though there's an applied force up. We looked at situations, I'm not going to redraw it, like this ramp. You already have it drawn if you decided to. I'm just going to copy it and throw it down here. We had situations where you have a pulley and two masses connected by some wire or string. Where what you have is a force of gravity acting down on one and a force of gravity acting down on another. We had situations where you have a countertop. We're going to have to wait for my computer to catch up. I shouldn't have done that. And you have an object on top of the countertop. attached with a pulley to another object that's going to be acted on by gravity. So we have something like this. And perhaps this object that's on the countertop has a force of friction between it and the countertop. Perhaps it doesn't. But what we have here, and I'm going to go to a full screen where I can get everything on here. What we have here are the following forces. We have a force of gravity down, and we maybe have a force of friction in this direction. We also have a force of gravity here, balanced by a normal force here. And I'm going to quickly label all of these forces, but you should understand that to analyze any of these, you're going to add those forces together and set it equal to ma. So this is an applied force. This is an applied force. This is a force due to gravity. Well, so is this, so is this, so is this. So is this. We have a force due to friction. We have a normal force. We have another force of gravity. I mean, the bottom line here, and I'm going to walk through all of these, if you take a look at this one, you would write ma equals applied minus force of gravity. If you look at this one, you would have ma equals force of gravity minus applied force. If you look at this one, you would have ma equals Fg parallel minus F of friction. If you look at this one, you would have ma equals the force of gravity acting on the larger mass minus the force of gravity acting on the smaller mass. This one, you would have the force of gravity acting on the hanging mass minus the force of friction on the table mass. And in all of those things I said, anytime I said force, I really should have said magnitude. You take the magnitude of one force minus the magnitude of the other force. That's what we did, and we did vertical motion as one day. We did ramps as another day. We did pulleys as a third day. And then I'm just also going to add in here the very final lesson, which was 11, I think. Yep. 2.11, true and apparent weight. Now, I'm almost done. I know that this is cutting into your review time, but it's very easy to finish this unit and go, oh, yeah, we did that? Because it's been so long. That's the unit about dynamics, forces, Newton's 3 laws of motion. But this unit is called dynamics and gravitation. There are a couple of other lessons that we looked at dealing with forces of gravity and gravitational fields. And 2.9 was Newton's universal law of gravitation. And you're going to be expected on your exam to be able to calculate gravitational forces and apply this formula for single pairs of masses or for 3 masses. Remember the quiz we had where we had 3 in a triangle? Or the questions we did in class where we had 3 masses in a row? You should be able to find the net gravitational force on any of those masses by finding the gravitational force on that mass by one of the masses, by finding the gravitational force on that mass by the other mass, and then adding those two gravitational forces. And if they are in a line, then you might have to add the forces by adding the numbers because the forces are in the same direction. If they are in a line, you might have to add them by subtracting the magnitudes because the two forces are in competing directions. And definitely if it's two-dimensional in the shape of a right triangle, you have to find the two forces, draw them tip to tail, and add them like we did on that quiz. And then 2.10 was about gravitational field strength. And I hate to boil 2.9 and 2.10 down to equations, but that's what they basically were, right? Everything else led up to all of this stuff, right? Which is there's a lot of thought going on here. It's not just grabbing a formula. Because in this stuff, when you're doing, say, this example, or this type of question, you have to figure out how to calculate the force of friction from mu. So there's all these moving parts to it. Here, I mean, it's basically, if you want to find the gravitational field strength, take capital G times the mass of the planet over the distance squared. One final reminder here, though. It's very easy to confuse these two formulas. The force has m times m. The gravitational field only has a single m. This is the source of the gravitational field. The thing I want to remind you is r is the distance from the center of the planet to that location. So sometimes you may have to add the radius of the Earth to an altitude above the surface of the Earth. Or if I give you a question where you're going in the opposite direction and you want to find the altitude, then maybe you have to calculate r first and take away the radius of the Earth. We'll talk briefly tomorrow about your exam on Friday. But your exam on Friday will contain approximately 25 questions, multiple choice and numerical response, same as we always have. I know that at least one or two of you have accommodations for extra time. I will just ask everybody, even though I know this, if you have that accommodation, send me an email to remind me to set that up. Okay? I'm going to hand out some review materials, and that's what we're working on for the rest of the week until Friday when we write our exam.